In this segment, we will study BRDFs and the reflection equation. This is the next natural step after considering the radiance and the irradiance. We first seek to build up the bidirectional reflectance distribution function of BRDF, which goes back now more than 40 years to this very famous paper by Nicodemus at the National Bureau of Standards. Prior to that time, there were various ad hoc ways of considering different material measurements. He unified them and introduced this notion of the bidirectional reflection distribution function. It is a function based on incident and viewing direction. It relates the incoming light energy to the outgoing light energy. The BRDF, or the bidirectional reflectance distribution function, is a unifying framework for many materials. Here I've shown some examples of materials we may have. On the bottom left you see these vases or pots, which are from the Advanced Renderman book. You have plastic, you have metal, you have matte. Historically, they may all have been represented with ad hoc formulae and ad hoc measurement approaches. But the BRDF provides a unifying framework for all of these different materials. In fact, about 20 years ago, Matuszek et al. Introduced this database of BRDFs where they measured spheres of different materials. Spheres are particularly easy for BRDF measurement, and they introduced this database of measured BRDFs of various materials in the real world to complement the analytic BRDF models that we had developed in computer graphics over the years and which you will be using in this course. The key point of the BRDF is that the reflected radiance from a surface is proportional to the incident irradiance. And the BRDF is simply this constant of proportionality. Therefore, it is a ratio of the outgoing light or the outgoing radiance to the incoming light or the irradiance. If we look at the equation which is written, the numerator is the outgoing radiance, which is a function of the outgoing direction. The BRDF is a function of both the incoming and the outgoing directions, and the denominator corresponds to the incoming irradiance, which is the incoming radiance times the cosine term times the incident solid angle. We can flip this around, and the BRDF enables us to get a formula for the reflected radiance, which is simply the incident radiance times the BRDF times this cosine term in the solid angle. Later, when we talk about the reflection equation, we will essentially be integrating that over all incident directions. Notice that the BRDF is a function of 4 variables, so it's a function of incident and outgoing directions, each of which depends on the latitude and the longitude, or more precisely the elevation and the azimuthal angles, theta in, phi in, theta out, phi out. The units of the BRDF is 1 over steradian, because radiance has units of watts per meter square per steradian, irradiance has units of watts per meter square. My graduate school colleague Simon Rysunkiewicz introduced this Brdf Viewer, where he was able to make plots of multiple different BRDFs. In this case, the diffuse BRDF is equal essentially in all directions. It's just a constant for the Lambertian BRDF. The specular reflectance models, Torrance-Sparrow is a very popular one, have a strong specular peak, and in fact towards grazing angles the specular peak is even more pronounced. These are all examples of what are known as isotropic BRDFs. There is no preferred direction around the surface normal. The surface normal is the only direction on the surface. There's no preferred tangential direction, But you can also have anisotropic BRDFs, which have more interesting shapes. Torrance-Sparrow is one physically based BRDF, which is more sophisticated than simple Lambertian and Phong BRDFs. It has the general form of microfacet BRDF models. It's based on this notion that the surface is made of statistically many microfacets or V-grooves that reflect light back to the viewer. It includes what is known as a Fresnel term for wavelength dependency. That's this term F here. The Fresnel term corresponds to a phenomenon that when you see a surface at a grazing angle, it reflects more specular light, so it behaves more like a mirror. You can test this phenomenon in the real world. There's a geometric attenuation term that corresponds to masking and shadowing of these facets. And then there is a distribution term that essentially says how rough is the surface. If the surface is perfectly smooth like a mirror, then you will essentially get mirror reflection. But for a rough surface, you will get a broader specular lobe that's determined by this D term. And these are normalization terms that correspond to how much of the macroscopic surface is visible to the light source and visible to the viewer. Notice that the Torrance-Sparrow BRDF is reciprocal in the sense that you can replace the incident and the outgoing direction and the BRDF won't change. This is a physical property of physical BRDFs, which is known as Helmholtz reciprocity. There are a variety of other BRDF models. One way is what I showed you with the spheres that Matuschik measured, where you can measure the BRDFs and build a 4D table. In fact, at UCSD, we have unique facilities to do this. We have a 4-degree of freedom gantry on which BRDFs can be measured. There have been many anisotropic models developed for hair and brushed steel. You can also have non-physically based BRDF models such as cartoon shaders or funky BRDFs. And we can capture spatial variation in the BRDF, so it can be a function of spatial location in addition to incident and outgoing direction. In general, the area of BRDF modeling has been one of the core problems of computer graphics, and it remains a very active area of research. It is one in which I have worked in over a large part of my career. Having defined the radiance, the irradiance, and the BRDF, we are now ready to put together the reflection equation, which is the core equation you need for direct lighting, and in fact is what you will need for homework 2 in terms of the core theory that is being developed. Let's say you have a point X that you want to shade because of lighting in some direction omega in, and the viewer is in a direction omega r. We can write down this equation, and I will explain the various terms. The LR term corresponds to the reflected light or the output image. It is a function of the spatial position x and the outgoing direction omega r. We then consider the emission term LE. This corresponds really to light sources in the sea. For most objects, the emission term is 0. However, for light sources, they are outputting energy into the scene, which will be a function of the spatial location and outgoing direction. What we are most interested in is the next term, which corresponds to the incident light from the light source, that's what Li is, times now the BRDF. The BRDF encodes what kind of a material you have and how much of that incident light is reflected to the outgoing direction. Times a cosine term, which is very important. You have to multiply by the cosine of the incident angle, and that is important in order to get the incident irradiance, which is there in the BRDF definition. That's fine, that's for one light source. What happens if you have multiple light sources? Well, using the linearity of lighting, we simply sum over all of the light sources in the scene. And indeed, you've done that already in your ray tracer in your earlier OpenGL assignments in CSE 167. But we can go a step further and derive mathematically what happens if there are an infinitely many light sources in the scene, Or more precisely, you have a map that tells you how much is the incident radiance for each incident direction. In this case, you replace the sum with an integral, and now you have to integrate over solid angles d omega n. Where does this Li term corresponding to the incident radiance come from? It is often represented using an environment map, which is light as a function of direction from the entire environment, and it can be conveniently captured by photographing a chrome steel or a mirror sphere, or in this very early work by Miller and Hoffman in 1984, they were photographing a Christmas lawn ornament. Now, once you do that, you can actually insert objects into the scene, such as the synthetic robotic dog, with the correct reflections in the scene. Notice that this has not been touched up, so the photographer is actually visible here and here. The environment map is strictly accurate only for one spatial location x, so it's a function of the incident direction omega n. However, for distant lighting such as the outdoors, the environment map remains the same at any spatial location or any scene locations. And it's a common approximation that even for relatively near field lighting, we use a single environment map. I also want to briefly mention Irradiance.Environment Maps, especially because I have a strong attachment to this. It is one of the key components of my PhD thesis. So the left image corresponds to the incident radiance or the illumination environment map. This is actually courtesy of Paul Debwek, and it is in the Grace Cathedral in San Francisco. Each point or each pixel in the environment map corresponds to incident radiance from a particular lighting direction omega n. If you wanted to shade an object, you would find the reflected direction for a mirror object and use that to index it to the environment map. The irradiance environment map on the right tells you the irradiance for each surface orientation. Each point or each pixel corresponds to a particular surface normal or surface orientation. You notice that the normals that are pointed up are brighter towards the light sources in the Grace Cathedral. Those that are pointed down see the relatively darker floor and they're darker. And we have this overall red and blue tinge from the color of the windows. In order to get the irradiance environment map on the right, you have to add up or integrate the contributions of all of the incident radiance on the left. My PhD thesis essentially showed how you can do this efficiently and have an efficient representation for irradiance environment maps that is now widely used in interactive applications such as video games. In summary, environment maps have been widely used as a lighting representation. They're essentially the input Li in the reflection equation. Many modern methods deals with offline and real-time rendering using environment maps. This is an idea of using an image-based representation of complex lighting in the scene rather than individual light sources. And then you can couple that with general arbitrary BRDFs in the scene.